Our first presentation is Senior Design 1, Group number 1, and they are going to talk about hydroponics. Okay, go ahead.
Thank you very much, Dr. Turkey. Hello, good afternoon, everybody. We are the Urban Gardeners, and we're working on the fully autonomous aquaponics system. So by definition, aquaponics is the fusion of aquaculture, which is the raising of fish, and hydroponics, which is growing plants in nutrient-rich water without the use of soil. So we want to automate our system in order to ease the usability. Using aquaponics can be a very difficult method to implement for those without the technical knowledge. So we would like to automate it by self-regulating pH, checking pH, self-regulating water temperature, and the water flow of the system. So we will be doing this by using an Arduino to communicate with our sensors and send the information through Raspberry Pi online through graphical representation in order to do so. So we have our basic team overview. We have here Mohammed Abedin. He's a computer engineer and our computer leader. Myself, Namdi Kosa, I'm an electrical engineer. Desmond Hickson, computer engineer. And Kevin Leos, also a computer engineer. And our advisor, Dr. Iyad Obeid. So here's our basic project overview. We're using the ebb and flow system, which our design basically starts with the heart of our system, which is the fish. The fish produce waste that is pumped through a water pump, through PVC tubing, to our grow bed. Our grow bed will hold the volume of our plants and will absorb all of the nutrients from the water, thus returning clean water back to the system in a continuous cycle. So we have our design plan for our proposed system here. We will start with the aquaponics system. Through our sensor array of the pH sensor, temperature sensor, and the water flow sensor, we'll communicate through Arduino and Raspberry Pi to send information online through graphical representation, as well as send user alerts to know if maintenance is needed for the system. So just like with any technical project, we have functional and non-functional design constraints. With our functional, as I stated before, we have the fish as the heart of our system. That without the fish, without the health of the fish and them in a comfortable environment, our project won't survive. So we would like to keep pH between a range of 6 and 8 and water temperature between 70 and 80 degrees Fahrenheit. Also, we'd like to minimize the power consumption. With a project like this, of course, we don't want the power output by the system outweighing the produce that we'll get in the end. So we would like to keep power costs low, as well as have a water pump working at a flow rate of 112 gallons per hour. Also, with our non-functional design constraints, we have costs, as I said before. We'd like to keep costs low. The size of our system, we'll be using this system, this ebb and flow system right here, a 2x2 foot grow bed, as well as a 20-gallon stock tank below it to keep our system, basically we estimated at 4 feet in height to keep it small for like home use and so forth. And also safety. With an electrical system like this, we like to, of course, provide safety. It's for it being a homegrown system, keep it safe and around other, sorry. So here's our basic overview of what we'll be discussing, all the different aspects that go into the system. We have the fish that we chose koi fish. We'll be growing lettuce in our system. We have the pH controller that will be regulating our pH levels. We also have the food dispenser that we'll be building, the temperature sensor that we will be building, and our water pump cycle, our light on and off sequence, and the data logging. So as I stated, we'll be using koi fish. Koi fish we chose because they're very durable through a wide range of pH and water temperature, and we felt that best for our system. Lettuce, we were able to talk to local aquaponic gardeners, and through research we were told that lettuce is the best growing plant in aquaponic gardens, so we just chose to use that for our system. Now, for our pH controller, we decide on implementing a system that comprises of 2 tanks. We'll have a tank holding a bicarbonate solution, whereas if our reservoir rises above a pH of 7.7 and becomes too basic, a pump can be activated in order to gradually pump in acidic solution to neutralize the pH. And whereas though if the pH were to fall below 6.3, a water pump would be activated to pump a basic solution into it to neutralize the pH as well. So we plan on building our pH sensor through using 2 9-volt batteries to power the system, a TL082 op-amp, a BNC panel connector to connect the circuitry to the pH probe and the pH probe, and a digital voltmeter through testing. So we have a scale here for the voltages output by the system. We have a 414 millivolt reading corresponding with pH of 0, a neutral pH of 7 being 0 millivolts respectively, and negative 414 millivolts outputting a basic solution of 14. So here basically, this is our schematic for the system. We have our pH sensor to the left hand of the schematic, and as I stated before, we're using an Arduino in our system, and with Arduino can only read in voltages between 0 and positive 5 volts. So, like I said in the last slide, we'll be dealing with a range from 414 millivolts to negative 414 millivolts. So what we plan on doing is using a level shifter to amplify voltage to which it will work to change voltages from negative 5 to 5 volts and keeping them in a positive range of 0 to 3.3 volts, which is perfect for our system. And then here's the physical representation of our system right here. We're having our op-amp in the middle here, the two batteries to power the system, our BNC panel connector, and a digital voltmeter for testing. So for the food dispenser, we plan on using a controller or a container with a drill bit through the container, pumping food out of the container through a period 3 times a day, once in the morning, once in the afternoon, once by night. A servo motor, an Arduino controlled servo motor, will control the drill bit to pump out the food as needed. We estimate that each fish needs to be fed 8% of their body weight a day. So with the fish we're using 4-inch koi fish, as their weight is at 12.6 grams. We estimate that our fish we need to be fed 1 gram feed per day. So now with the temperature sensor, we're using a TMP36 temperature sensor transistor. How we'll build it is we'll use the temperature sensor, a lead pipe to enclose the circuit, a silicon gel to enclose all of the wiring into the circuit, and we will solder wires to the 3 legs of the circuit and enclose the entire system in the lead pipe, only putting the head of the temperature sensor in the water. So in this picture you can see this is the transistor we'll be using. We'll be using a 5-volt input to the left hand side of the pin, leftmost pin. Ground will be attached to the rightmost pin, and our analog voltage will give us our reading. So what we have here is now just basically a test of the system at room temperature, giving a voltage of 763 millivolts, which corresponds with room temperature. Through this equation down here, we get room temperature at 26 degrees Celsius. So we'll be using a relay to control the light on and off sequence for our system. We're using the power switch tail 2 relay in order to control light on for 18 hours for the lettuce and off for 6 hours. Just through talking to the aquaponic gardeners, they just told us that this is sufficient lighting for the plants and will have our plants grow sufficiently. So we chose to use this relay because it connects directly with 3-prong household outlets, and we'll build it by attaching our T5 fluorescent T5 lights to the relay, connecting it to the wall, and it connects directly with Arduino, so we can control the sequence and the time constraints through that. And now for the water pump, well, as I said before, we'll have our flow rate at 112 gallons per hour. We were told that we want the entire volume of our stock tank to go through our grow bed every hour on the hour. So we calculated the time for the pump on at 11 minutes every hour. And now for our data, the input to the Arduino is analog. So like the analog voltages we'll be getting from the TMP36, from the pH sensor, all the voltages will be going into the Arduino. All that information will be converted into digital signals going to the Raspberry Pi and getting ready for graphical representation to be put online. The Raspberry Pi will also save all of our information and put all the data online for us to read. So this is basically our software block diagram of how the software will work. We have our initiate variables and define IO port state, which will be able to define all of our variable names and the different IO port configurations we'll be using. In the main loop, we have define current time, which will convert hours to minutes and seconds and defining specifically what we want as far as each pump, how long we want each pump to be on for, how long we want the lights to be on for in seconds and minutes. In the check pump and light sequence, this will now just initiate when to start the sequence, when the lights should go on, when they should come off. Our pulse sensors will save all the information that we're getting from the Raspberry Pi, or from the Arduino, and then it will be sent to the Raspberry Pi to then be sent out online. So with all the different components we will be using, we estimate the power consumption to be at 76 watts, around 76 watts. This is our bill of materials. We had a few things donated to us from local aquaponic gardeners from Healthy Gardens and Supply and Boyer Gardenings. We had the ebb and flow system donated, as well as the clay pebbles we'll be using in our system, and the round mesh pots we'll be using to grow our plants in. Here's our basic schedule of what we've done so far, the meetings we've been to, what we'll do in the summer, as well as continuing on in Senior Design 2. And basically in Senior Design 1, we've done the research to be able to build our conceptual design for our system, the software design, all of the schematics and the framework that goes into building the pH sensor, the temperature sensor, and we've come up with a full design document. And in the summer, we plan on building the physical system, starting to test pH, water temperature, the water flow rate, as well as begin growing plants. Are there any questions?
Any questions?
Dr.
I have two questions. First question is, you can't eat koi fish, right?
No.
Okay. Would there not be an increased efficiency from your system if you use an edible fish? Have you considered that?
We, for our system alone, just because koi fish, at least for Senior Design, won't grow too big for our system. If we, first, let's say, used like an 100-gallon tank, we'd be able to use tilapia, which of course is an edible fish. It's just for our system being so small, we didn't want to use a fish that grows too wide, too big for a 20-gallon tank.
Okay, so my other question is about the lighting.
Okay.
You're going to use fluorescent lights, which I understand are fairly power hungry. Is that, I don't know if that's correct, but could you use like LED lights or something which are bright but don't draw as much power?
It's not that we speaking with aquaponic gardeners around the area, they told us that LED lighting provides, I believe it was too much heat, high power sodium lights. So they'll provide too much heat.
No, sodium lights will, but not LEDs. LEDs like have no heat.
Okay.
But I don't know if like they have like the right spectrum of light or like enough power, or like I don't know what their deal is, but I know they consume a lot less. That's why they consume less electricity, is because they're not wasting a bunch of it as heat.
With the heat.
So I didn't know if that was an option for you, because you might be able to like dramatically lower the power output of your system. But again, I don't know anything about gardening, so I don't know if that's an appropriate substitution. Something just to consider.
I mean, even like kind of what you were saying, another reason why we didn't choose LEDs was just because when we were talking to, like you said, the aquaponic farmers, they said, like you were saying, it doesn't necessarily cover the red spectrum. And if you put it in a system, it like drastically decreases the yield of plants that you get. So the bicarbonate sodium lights are too high power for our system.
Sure. And
kind of the LEDs will take a longer time for us to grow like the plants that we need. So they said the fluorescent lights are the exact kind of lighting that we need, that doesn't consume too much power, and also at the same time produces an acceptable rate of yield. So.
I think they use it also to generate heat, right? To maintain the temperature.
What, fluorescent?
No, the sodium light.
Oh, sodium, yes.
So does it really have to run like for 18 hours, or you can just...
I mean, through testing, we'll probably be able to see whether we can minimize the hours of them.
But what is industry standards? Like typically when we have this in a commercial operation?
It was the 18 hours. And
It was around 18 hours?
That's what the standard was.
Okay. Now, going back from the last presentation about the number of gallons per hour, which is 112 gallons, right?
Yes.
Is that for this tank or for the commercial tank?
That's just for our specific tank.
Okay. Now, if you break it down per second, that would be around 130 milliliters
Yes.
per second. That's a high flow, and it's a it may actually break down the pump running like for 24 hours, you know,
That's
how
not
long
right.
it's working?
It's not
It's not
really-
running 24 hours.
How long it's?
Well, on the slide that we have.
Yeah, it'll be running for 11 minutes every hour, but
So 11 minutes per hour, and in this 11 minutes you have to pump it 112 gallons?
now pump the full volume of our stock tank to our grow bags.
So what is 112 gallons?
That's just how fast it's.
Okay.
We're not pumping, it's 100.
So how many
We're pumping 20 gallons into the system.
every hour?
Every
Every
hour.
hour.
But the pump capability is 112
Every hour.
gallons per hour. Okay, so maybe you can make this clear. Any other questions? Go ahead.
Could you grow any other plant beside lettuce?
I mean, yeah, we looked into growing, I think it was tomatoes, and it's better to grow like fully like leafy greens as opposed to let's say apples or not apples. Something is better with vegetables, leafy vegetables. At least.
What would be the labor saving per tank? Once you have your system up and running, like, and they have a commercial tank, what would be the amount of labor saving per tank? Like how
Labor
much
saving?
human labor you'll save by having the whole system automated?
I mean, for our system, probably not. Like
Not, you know, once you put it.
once with future work, we've seen articles where in Japan right now they're building a vertical, fully hydroponic system where it's just floors of gardens. So I mean, in the scope of our project, the motivation for our project is reducing the need for arable land space and being able to garden, like do gardening in urban areas just like Philadelphia. So I mean, the future work is probably outweighs the household.